Okay, we're going to talk about geometric probability, and in order to just make sure that we're all kind of on the same page and talking about geometric probability before we discuss that, we want to discuss a little bit, making sure that everybody has a clear understanding of just probability overall and what that means. So we're going to talk a little bit about probability. And in order to do that, we need to make sense of some basic stuff. So let's talk about this problem. You've got a fair coin is equally likely to land heads up or tails up. So what that means to be a fair coin is that it's not weighted, it's not a trick coin, it's not going to necessarily land on one side or the other more often. So both sides have an equal chance of coming up. And then we're going to take one fair coin and toss it 3 times. And what's the probability that the coin will land tails up exactly twice? Okay, so let's think a little bit about what that means, and we're going to draw it out. Kind of laying it out in a diagram is typical with probability sometimes to understand. So let's assume that on the first toss, right, your coin could come up heads or tails, right? And then on the second toss, after getting, let's say, heads the first time, maybe the next time you get heads or tails, or if you got tails the first time, again, you could get heads or tails again. And on the third toss, again, each time you could get heads or tails on the third toss. So we could have heads or tails there, and heads or tails again, and heads or tails again. And what I'm looking for, remember, is the probability that it comes up exactly twice. So I'm looking for a pathway where we're looking for 2 T's and 1 H, right? So I tossed it the first time and I got heads, and then heads again, and then heads again. So that one's no good. And then heads, heads, tails, that's no good. Heads, tails, heads, no good. And then heads, tails, tails. There we go. That's the first time when we see that we got exactly 2 tails, right? And then we're going to take a look at the other possibility. If we got tails first and then heads, heads, that's not what we're looking for. And then we got tails, heads, tails. That's tails exactly twice right there. So that's, again, 2 tails. And then we get tails, tails, heads. Again, that's exactly twice, right? And then in the last situation, we got tails, 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 which is not what we're looking for, because remember, we wanted it to be exactly twice, not at least. So when we write this, express this as a possibility, what we're looking at, probability, is the likelihood that an event will occur, okay? And that means we want whatever the successful outcome, the favorable outcome would be the desired outcome, okay? If I could spell desired right, that would be great. D-E-S-I, the desired outcome, is what we call a favorable outcome, whatever it is you're looking to have happen, right? And in this case, the probability for our particular problem was tails exactly twice. Okay, and then the favorable outcomes or desired outcomes is divided then by the total possible outcomes, the total number of possible outcomes. So here comes the total number of outcomes. The desired outcome was how many times did we get tails exactly twice? And that was 3 times in this situation above, right? We got it 3 times exactly twice. The total possible outcomes is, remember, we had heads, heads, heads. That was 1. Heads, heads, tails, 2. 3, 4, 5, 6, 7, and 8. So that's 3 divided by 8. That's the probability. If you toss a coin 3 times, that's the probability that you would get tails exactly twice. And that's kind of the basic idea of probability. A lot of times we'll lay it out in a diagram to see if we can make it make sense. But we're going to talk about geometric probability, which is slightly different, obviously, because in geometric probability, you're trying to draw it in a picture a little bit. So geometric probability, we're going to talk about 2 types. We're going to talk about a linear geometric probability, where you talk about points on a line segment, and what's the probability that a point lies on a specific line segment, and that's what we'll talk about right here. And then we'll also talk about geometric probability as line in a region, and so that's coming up in just a minute. In general, when we talk about, let's say we have point S on segment AD, we're going to choose that at random, and it's somewhere. That means it's somewhere on segment AD, and we don't know where, and we want to know what's the probability that S is potentially on segment BC. So here's BC, starts at B, ends at C, all points in between. point S is somewhere on here. We just don't happen to have any idea where, right? Okay, and if we want to know the probability that S lies on segment BC, then what we're going to do is we're going to say the length of BC divided by the length of AD will tell us the probability that point S lies on segment BC. All right, so same thing. Here's an example exactly of what we're talking about. We've got point K on segment ST. So let's take a look at segment ST. From S to T is here, right? Point K is somewhere on here. We just don't know where exactly, but it's somewhere on here. And we want to know what is the probability that K lies on segment QR. So starting at Q, ending at R, and all points in between, what's the likelihood that it lies somewhere in here, right? So we want the probability that K lies on segment QR, right? Which means we're going to divide the length of QR by the length of ST. The length of QR, the distance from 5 to 8 is 3, right? Remember that you can subtract 8 minus 5 and take the absolute value, or 5 minus 8 and take the absolute value. Remember that distance is absolute value. Divided by the length of ST, and obviously you can either count it on the number line, or you can subtract 2 minus 14 and take absolute value of 14 minus 2. That's 12. So the probability that K lies on segment QR is 1/4. A lot of times we represent probability in the form of a fraction, or sometimes as a decimal, so that would be 0.25, and that's exactly 0.25. And a lot of times we'll represent probability as a percent, so 25%. We have a tendency to represent it all of these different ways, and you just want to pay attention to whatever you're asked to do. Sometimes you're going to be asked to express it in a fraction, sometimes as a decimal, sometimes as a percent. So just make sure you're reading directions very carefully in that instance. All right, so here's another example of laying out a geometric probability in a linear fashion. So we have Elena's bus runs every 25 minutes. She arrives at her bus stop at a random time. What's the probability that she's going to have to wait no more than 10 minutes for the bus? So we're going to have a segment that represents the time. We're representing time in a really linear fashion, the time between the time that it takes for the bus to come again. So it's come at the first time. You have a bus that has come to the bus stop here, and then 25 minutes has passed, and you have another bus coming along there, right? And then Elena comes up, and she's waiting, and we want to know what's the probability that she's going to have to wait for no more than 10 minutes. So she's waiting a time span, let's say a random time span of about 10 minutes, right? Okay, her wait time. So we want to know what's the probability that Elena waits no more than 10 minutes. And I definitely probably wouldn't write that out on the usual basis. Okay, so we have a 10-minute time span, right? And then we have a 25-minute time span between buses. So that probability is going to be 2/5. Or as a decimal, that would be 0.4, right? Or 40%, excuse me. Just depends on what form of answer you're kind of asked to express that in. That's a really very, very basic problem about probability, geometric probability in a linear fashion with a bus. Obviously, that's not kind of a typical question with probability about a bus, because the bus has to stop and wait for Elena to get on the bus, and wait maybe for other passengers to get on the bus. So typically, there's a wait time in between, but we're just talking about a very, very basic form of probability, and we're not taking all those other things into consideration right now, primarily because we're going to be thinking about some geometric probability slightly differently, much more as it's related to what you've been studying in this particular unit about area. So we want to talk about geometric probability in terms of area. And in terms of area, the probability of an event occurring in a geometric probability is the area of the favorable region. Remember, this would be called a successful outcome. Right? This is what we want to have happen, divided by the area of the entire region, however much space you have all together. So let's take a look at this first one. We have a circle inscribed in a square. Point Q in the square is chosen at random. What's the probability that Q lies in the shaded region, right? So the shaded region, is all in this space. That's what we're looking for. What's the probability that it lies in this shaded space right here, right? All right, so in order, let's express what that looks like. So we have the probability that Q lies in the shaded region is going to be equal to the area of the shaded region divided by the total area of what you're looking at. So it could be, in this case, that would be the square, which is the maximum, the outside figure, outside most figure. So area of the shaded region divided by the total area. All right, so how are we going to find the area of the shaded region, right? So the area of the shaded region, it's kind of like rolling out, maybe like rolling out a square piece of dough, let's say, and then using a cookie cutter and cutting out that massive circle in the middle and getting rid of it, and then you have these little corner pieces left over. So how would we find that area? That's what we would have left over if we take the area of the square and subtract the area of the circle, right? Divided by the total area of the square. So you remember your formula for area of a square is s squared, s represents the side length, divided by area of a circle is pi r squared, excuse me, that should say minus pi r squared divided by the total area of the square. So what is the side length? We're given the side length of the square. That's pretty useful. That's the value of s. Right? So 6 squared minus, okay, now I'm stuck. I don't know what the actual radius is. So let's figure that out. The center of the circle, if the circle is inscribed in the square, should be the same as the center of the square, right? So if the whole entire side length of the square is 6, then that means that the radius of your circle should be half that. That should be 3. That should kind of make normal sense. Think about making a kind of smaller square in here. Minus pi times 3 squared. So we'll put that radius right in there, all divided by 6 squared. And then we get 36 minus 9 pi all over 36. And as an exact value, that would be, if I reduce it and divide every term by 9, then I'd get 4 minus pi all over 4, right? That's kind of a strange value for us to express in terms of a probability. So it's much more likely that we would express our probability if you type into your calculator 4 minus pi divided by 4. Please make sure that if you're going to type it in as a single expression, you would put parentheses around that numerator 4 minus pi before you divide. And then your approximate probability, so your probability that Q lies in the shaded region as an approximation would be 0.215 to the nearest, that obviously that's the nearest thousandth. If you had to represent it as a percent, then I'd say 21.5%. Okay, please make sure, as always, that you're paying attention to your directions as to the form of answer that you're asked to express it in. All right, last one's a little more complicated. We got a target. We have an archery target. We have 5 colored scoring zones, yellow, red, blue, black, and white, formed by concentric circles. The target's diameter is 122 centimeters. Radius of the yellow zone is 12.2 centimeters, and the width of each of the other zones is also 12.2 centimeters. So the band for each color is 12.2 centimeters. So if an arrow hits the target at random point, what's the probability that it hits the red zone? So we want to know what's the probability that it hits the red zone. So we're going to say the probability that the arrow hits red, right? Which means that our successful outcome is, in fact, the area of the red band, if you want to call it a ring or donut shape. That's pretty much what we're talking about right there. The area of the red band divided by the total target area. Okay, so let's talk about how we're going to get the area of the red band, right? The area of that red band, the red contains the yellow circle and also the red band. So let's take a look at that yellow circle. So let's say we have the yellow circle, right? And I'm just going to blow it up a little bit so that we can see it a little bit better. So this is going to represent the yellow. We're going to fill that in a little bit with some yellow so that we can see it a little bit better. Here's the yellow region, right? Yellow region has a radius of 12.2. So this is 12.2 centimeters, right? And then we have the red circle, the red band that is around that. So now we're going to have to, again, start at that center, and we're going to increase this. So the red kind of contains the yellow, right? Okay, we're going to shade that in also a little bit differently. I'm just going to have to use the pink a little bit here, okay, to represent that red piece. But that's what we're looking for. And this also has a width of 12.2, right? 12.2. So if we want to know what the area of the red band is, what that means we're going to have to do is we're going to have to actually subtract, right? Because we have a circle that contains the whole entire thing. And again, we're punching out the yellow. So the red circle contains the whole entire thing. And then we have to take away the yellow circle from it to get what we're left over with in this shaded space right here. So in order to do that, we're going to do the area of the red circle, full red circle, right, containing the yellow, minus the area of the yellow circle divided by the total target area. Okay. All right. So how do we find the radius of the red circle? That should be the entire radius. So remember, you're coming from the center of your target all the way out to the outer edge here, which means that radius should be 12.2 twice, because you had a radius of the yellow circle of 12.2 and each bandwidth is 12.2. So this should be 24.4, right? Okay, so we have 24.4. And remember, your formula for area of a circle is equal to pi r squared. So we're going to have pi times 24.4 squared minus the area of the yellow is going to be pi times 12.2. This pen would stop doing that. 12.2 squared divided by the total target area. All right, well, that means we need to also know what's the radius of our whole entire target. Remember, we had a diameter of 122 centimeters, which means our radius is how much? Our radius then is 61, right? 61 centimeters. So then we're going to have divided by pi times 61 centimeters. Okay? So we're going to do 24.4 squared, which is 595.36 pi, minus 12.2 squared is going to be 148.84 pi divided by, and 61 squared is 3,721 pi. If you want to go ahead and cancel out all the pi, remember every single term has a pi, so you can go ahead and cancel that out. And then 595.36 minus 148.84 is going to be 446.52 divided by 3721. It's unusual that we would leave that as a fraction, and that's going to give us 12%. So that's exactly 12%. Would be the probability that the arrow hits the red circle. Got it? And that's it. All we're going to do for geometric probability now.